In this video, I'm going to show you how I built an interactive AI-powered data visualization dashboard using the brand new GPT4o model from OpenAI with very impressive performance and especially speed being anywhere between 2 or even 3 times faster than the previous version of GPT-4. And here we are using this model as a reasoning and planning engine for our dashboard, taking in a user question about the data and then figuring out how we can retrieve the necessary data from our database to answer this question, but also figuring out an appropriate way to visualize that data. And then finally we can use these instructions from the language model to retrieve the data and render this full-blown dashboard for our user. If you're new here, I'm Johannes. I'm an independent consultant helping companies discover and build out their use cases using these latest and still developing AI tools. And on this channel I create tutorials using the various methods and experiments that I come across with my clients. So let's get into it. So here's our data visualization UI, and it's connected to a database where we have some historical cryptocurrency trading data, and here the user can type in questions about those historical prices as well as trading volumes. And so starting with this first simple example, just getting the last 30-day prices for Bitcoin, the first thing you'll see here is this query plan being generated, and this is our language model looking at the user inputs and figuring out this plan that consists of one or more of these tasks. And for each task, there's a query that the language model has written to get the necessary data from our database. We also have this visualization type where the language model chooses the appropriate type of visualization to use. We have a title for the visualization, which we can see here. And then finally, we have some parameters that are going to be different depending on the type of visualization. So here for the bar chart, we just have this bar mode that determines whether it's a clustered or a stacked bar chart. Of course, here you can't really see that because we only have one value. We just have the one Bitcoin price value here, but you'll see that in the following examples. Later in the video, we'll also go through exactly how we can get the language model to reliably output this kind of plan structure, as well as then how we actually use this plan to carry out the visualization task, run the query, and finally render the results in our UI. But for now, this is just a rough overview of how the application works. So moving on to our next example for daily volumes for both Ethereum and Bitcoin in March 2024. And here now you can see this clustered bar chart in action because now we have the Ethereum and Bitcoin prices in the same chart. But we can also play around with this a bit more. So we can have it as a stacked bar chart instead. And also, like I mentioned, this plan isn't limited to just one visualization per request. So we can also get a separate charts for each of the cryptocurrencies. So now when we run this, we should actually get not one but 3 of these tasks, and then that's going to give us 3 visualizations like so. And so then looking at this plan in more detail, for the first one we now have the bar mode as being stack, including both Bitcoin and the Ethereum values. And then here for the 2 other ones, we just have Bitcoin for this one and just Ethereum for this one. And now we are also not just limited to bar charts either. So to push it even a bit further, we can also get total March volumes for Bitcoin, Ethereum and Solana in a pie chart. So now we should get one more visualization here like so. And looking at that addition in our plan, we have a different visualization type now of pie charts. And the way we have defined the pie chart in our code, it actually doesn't need any parameters. So then for this task, the parameters is just an empty dictionary. Now finally, we also have some forecasting capabilities here in our application. So if we go for this one, we get a forecast of Solana prices for the next 7 days. So here the forecast is on the red dashed line. And then we also have the historical data for the 14 days before that. And for this one, another different visualization type of forecast. And for these forecast tasks, we have 2 parameters that we can define. One being the number of days, so how long into the future do we want the forecast to be projected? And then also which prediction method or model do we want to use for that forecasting. And here we didn't actually specify any method, so here we just have this ARIMA as a default selection. And probably it doesn't make any sense for like actual realistic crypto market analysis. but it's a very standard forecasting method for this kind of time series data, so I'm just using it here for demonstration purposes. And so again, we can go a bit further here with this forecasting example, and we can add here to also get a forecast for Ethereum, let's say next 10 days based on the last 21 days. And let's use not only ARIMA, but also exponential smoothing, which is another pretty standard forecasting method, which I have also made available here in the application. So now we should get 4 different tasks and 4 different visualizations. We can already see here the different prediction model parameters. And looking at the visualizations, now we have the Solana, 2 forecasts, ARIMA on the left, and then exponential smoothing on the right. And then down here, the same for Ethereum. Very good. And so now finally, to push even further and really seeing how well the language model can do in constructing these pretty complex plans, let's also add Bitcoin here. So now we should get not 4 but 6 of these forecasting tasks in a single request, and let's see how well that does. So far so good, and it's still impressively fast, less than 5 seconds using the GPT4o model. And indeed here we have Solana and Ethereum like before, but also Bitcoin now at the bottom. So that basically covers what this application can do in its current form. So now let's look at the code that makes all of this possible. So first things first, we'll set up our connection to our database, and we are using Timescale as our database here. And Timescale is a Postgres-based database offering. And the reason I like Timescale is because it allows us to work both with this kind of numerical and time series data, but it can also be used as a vector store. So if we wanted to do something like adding some crypto market news and create vector embeddings and do something like vector similarity search on those news, we could include that also as part of our application using just that same database. And like I said, it's a database built on Postgres, so we can use this standard Python library for interacting with Postgres databases to also interact with Timescale. And so here we are just using this library psycop G2 to create the database connection using our Timescale connection string. And then using that connection, we can create this cursor, which is the object that's actually going to allow us to execute queries against the database, like we do here, cursor.executes in this get table info helper function. And this is actually very important because we are going to use this later on in constructing our prompt for the language model, because of course, in order to generate correct SQL queries, the language model will need to have information about our database and the data that's in the database. But we'll get to that part in just a moment. For now, if you wanted to replicate this using Timescale, they do have a 90-day free trial for their product, and you can find a link in the description for that. Now, if you use the link and you'll find yourself in the Timescale console after signing up, then here in the services, where you can already see I have a few databases running, but if you just sign up, then you'll need to create a service here. And you can either choose this serverless option, but then for time series use cases like this one, you'll probably want to select this one on the left instead. And then we'll select our region, the amount of compute and memory. We don't need all that much, especially for this demo, and then just create the service here. We don't need this config file. The only thing we'll need is this connection string here. So we'll copy that, and then we'll just need to wait a few moments for the service to finish being deployed. In the meanwhile, we can take this connection string and add it to our environment variables, and now our service is already ready. So now moving on to this load data.py. Here we are just loading the data we have from these CSV files, which I have exported from coinmarketcap.com. Of course, if you wanted to implement some kind of real-time querying against some real-time crypto market API, you could do that without too much extra effort. But here we are just working with these data dumps instead. And so we are reading all of those into a pandas data frames. We are adding a new column for the symbol of each crypto, so Bitcoin, Ethereum, and Solana. And then we are combining all those individual data frames into just one data frame. Then we'll be creating a table for our crypto data with a date field, the high price for that day, so the highest price the crypto has in a given day, the lowest price, the closing price, which is the final price when the day closes, so at midnight, and this is the closing price for the crypto on that day, the trading volume in US dollars, the total amount that's sold and bought during that day, and then the symbol that we added here. And then after creating the table, this part here is simple but very important. We are adding these comments on each of the columns to describe what exactly is there to describe what the column is, what data is in the column. And again, this is going to be important for passing this information to the language model. So that's why we want to add these comments. And next, after creating the table, we are going to convert that table into a hypertable. And the hypertable is a concept in Timescale, which applies to time series data, where essentially it's going to partition that data, that table, under the hood in the database architecture by date. And we don't really need to think about this too much. It's not going to affect the way we do our queries against the database in any way. But this partitioning simply means that when we run time-based queries against the table, they are going to be much more performant and much more efficient. So for this create hypertable, we are just passing the table that we want to convert, and then the date range on which the partitioning is going to be based on. So then using our cursor, we're just going to execute these two queries, creating the table, adding the comments, and creating the hypertable as well. And then after that, we can iterate over our data frame of combined crypto data and insert each of those rows into our table. And then finally, this connection.commit is just going to ensure that those changes persist in the database, that they get saved in the database. So that's important as well. And then here at the very end, we're just going to print out this get table info, this helper function that you saw earlier in the database.py, just so you can see what the output from that function is going to look like. So now we're going to run this load data file against the timescale service we just created. So Python load data.py, and that's going to create the table and then iterate over the rows. For these many rows, it's not the most efficient way to do it. We could do some kind of batch uploading, but it's not the end of the world. It's still not going to take too long. And so that's finished. And here at the end, you can also see the output from this get table info. So this is what that looks like. It's just a string that we'll later on include as part of our prompt with the table. And then for each column, we have the column name, data type, and then the description or the comment that we added. And of course, if we had more tables for our use case, we could modify this string to get all of those in this one string and give the language model all the information about the database all at once. But for now, we just have this one crypto data table. So that's our database all set up. And if we go to the Timescale console, to the services, the service we created, and in the Explorer, we can now see this new table that has been created with the columns. And although the row count here is still showing at 0, I'm pretty sure the data is correctly there. If not, we'll find out soon enough. And now we can move on to our main application file, which is here in this app.py. And this is where most of our actual application logic is, including the visualization planning and the visualization and the Streamlit UI. So we're just going to start by looking at the Streamlit UI first and then move from there. So as you will remember, our UI is pretty simple. We just have this title here, input field here, and then these buttons here with these example questions. So here we're just first initializing the user input as an empty string, the title here, input field here, and then the buttons here. And then as soon as we get some input, whether from the text field or the buttons, we're going to start this process of generating the visualization plan. And this is done with this function, async generate visualization plan. And it is an async streaming function because, as you saw, we are generating the visualization plan in real time, incrementally, as a streaming response from the language model. So that's why we need to run it by using async io.run. And this function takes two arguments. The first argument is the table info that we talked about previously. And then the second argument is the user input. And looking at this function, for the most part, it's just a pretty standard OpenAI chat completions create call. We are using the GPT4o model. We have two messages. We have a system message where we have a bunch of instructions for the model about how to generate the visualization plan. So you return a visualization plan consisting of tasks. Each task consists of the Postgres query to get the data that's necessary, the correct visualization type, and here we tell the model which types are available with the required parameters. And then some information about the parameters. Pie charts require no parameters, bar charts require a bar mode, either a group or stack, and forecast tasks require number of days and the prediction model to use. We also have some example parameters here, and reiterating the model that you will not return a visualization task with empty parameters, because although I have found this to be pretty reliable, returning the correct plan, I would say more than 90% of the time, The one thing that the language model sometimes doesn't get right is that it sometimes returns empty parameters for a bar chart or a forecast, which is not going to work out. So we're just trying to reduce that error by adding this here. And then for forecasting tasks, the way it's built right now, which you'll see in a second, is that we can only ever forecast a single value at a given time or in a given task. So if the user asks for multiple different values to be forecast or for multiple different cryptos, they need to be separated into separate tasks instead of trying to combine them. Then for writing the Postgres SQL queries, we have a bunch of additional instructions as well. Aggregate when possible to return only the necessary amount of rows. Never get all the columns, only get the columns that are needed to answer the question. Only use the column names you can see in the table information. Be careful not to query columns that don't exist. And this is mainly relevant if we had more than one table in our data. Pay attention to which column is in which table. If the question involves today, including things like last 7 days or last 30 days, I use the Postgres current date function to find out what the current date is. Always include the symbol for the crypto symbol in the query. And then this one is important. Always use the alias value for the numerical value for the query, because sometimes we might be getting the trading volume, sometimes we get the high price, the low price, the closing price. And the way our visualization functions are defined, it's going to be difficult if we don't know exactly what the column is called for the data that we should visualize. So that's why it's important to tell the model to always give this alias to the numerical column, so that then in the visualization functions we can always safely assume that the data we are going to visualize is found under a column with this name value. And then finally, when you ask these LLMs to write code, often they're going to include this markdown formatting for those. So like this, with these triple ticks and programming language for the code. But of course, this is going to give us an error if we try and execute this kind of a string. So instead, we tell the LLM just to return the query itself, like so. And then cherry on top, just think step by step before writing the query plan, which should give us a slightly better responses in general. So that's our system message. And then the user message is just going to be this very simple template, which is where we pass in the user input, so the user question, as well as the table info. So use the following tables, and then the table info will get placed here. And so that's it for the messages. And because we are wanting a streaming response, in real-time streaming response from the language model, we have this stream equals true here. And now this next part is probably going to be something that's unfamiliar to most of you. And this is where we are going to be using this powerful library called Instructor, which has really blown up in popularity over the last few months. And basically what Instructor allows us to do is define this response model as an additional parameter in our OpenAI chat completion, where we can define a specific predetermined structure that's then going to tell the language model that the response it gives us should fit exactly into that structure. And so in this case, the structure that we have defined is this visualization plan, and it's a class. And the structure that this kind of a visualization plan object should follow is that above all, it contains a list of these visualization tasks, which is another class. So there's a bit of a nested structure action going on here. And this task structure is then the place where we define these attributes that we have seen before. So the query, the visualization type, title and parameters, including descriptions of each field. And we also have these executable methods for this class, which are going to be very useful later on. But for now, the main thing to understand about Instructor and what we are doing here is that when we have this visualization plan consisting of tasks defined, and we send that to the large language model, it's going to tell us that whatever response it gives us should fit into this kind of a structure exactly. And this also comes with automatic validation, so that if for whatever reason the model gives us something different than what we are expecting, we can immediately raise an error and show exactly what went wrong. And this just gives us a lot more confidence in that we can know that whenever this function runs without errors, we can know exactly what we are getting. And compared to just working with string outputs from the language models, this is very powerful. And so then the way we use Instructor is very simple. For the most part, you're just using your OpenAI client as you would normally. So here we are using the async OpenAI client from OpenAI to get the streaming response. And you can define the client just like you would regularly, with the only difference being that here we also import Instructor. and then we wrap our client into this instructor.patch method, and then we can carry on using our client just like normally, except for the fact that now we can also start using this response model parameter. And another thing to note here is that our desired structure is also wrapped in this instructor.partial class. And this is just something that's going to allow it to also work with a streaming response from a language model, and so that we can continuously validate the correctness of the visualization plan even before it's actually complete. Whereas if we didn't use this partial class here, it would look at the partial response, look at the missing fields, and immediately throw an error because those missing fields are a necessary part of the structure. So that's a general intro to instructor and structured outputs. I know it might be a lot to take in, especially if you are perhaps not even so familiar with using classes, even outside of LLMs. But even if that's the case, I highly recommend you look into it more, because as I said before, being able to work with these predefined models instead of unpredictable string outputs, it's a real game changer when it comes to building any kind of LLM applications. And as you can perhaps imagine, you can use it for a lot more than just query planning, which is a use case I like in particular, and I made a previous video about it as well using Instructor. So if you want another example of how you can use it, feel free to check out that video as well. But for now, hopefully that makes sense, more or less. Now we can move on to actually executing this visualization plan once we get it from the language model. And this is where these various executable class functions are going to come in. So as you can see here, each of these tasks has these two methods. One is to execute the query, which is going to run the SQL query against the database using our cursor, fetching all the results. And then secondly, we have this run method, which is going to use that execute query to get the data, and then use that data to get us the correct visualization depending on the type of the class. So if it's a bar chart, we're using this get bar chart function, which I'll show in a moment. For a pie chart, we have its own function. And also for the forecast, we have this get forecast chart. And for any of these functions, we are passing the data that we get from the executing the query. We send the title that the model has given for this visualization, as well as any of the parameters, depending on the visualization. The forecast in particular is a bit more complex than the others. So we have these two parameters that need to get passed, as well as the column names from the SQL query, which we can get by checking this cursor.description, which is going to contain information about the latest executed query. So because we never quite know what the columns are that are going to be retrieved in a given query, they are dynamically generated depending on the user request. So we can't quite know what the columns are going to be. So therefore we always need to check them from the executed query description. And so then, regardless of the exact visualization, all of these functions return a figure object, which is a class from the Plotly graph objects module. So all these functions that I'm going to talk about a bit more in a minute, they all return this graph objects figure type. And this is good because this is something that we can very easily render in Streamlit. And so when we look again at our visualization plan, we also have this method here on the top level to run the plan, which just iterates over all the tasks in the plan, gets this figure from running each individual task, and then renders that figure using this streamlit.plotly chart with the figure passed to it. And all of this here is just to make sure that we are rendering them in the way that you saw in the UI. So we have 2 visualizations on a given row and as many of those rows as necessary, because again we can get 1 visualization or we can get up to 6. So these lines of code just determine the correct amount of columns and the correct amount of rows that are necessary depending on how many tasks are in the plan. And so given that our plan has this run method to execute all the individual tasks and render them in Streamlit, this puts into context the rest of our Streamlit code, which isn't much, but simply once we get the visualization plan from our call here, we print out the plan in a JSON format to debug it in case something goes wrong. We also write it out into the Streamlit UI, as you will remember. And then just by calling this run method on our visualization plan, then that's immediately going to render all of those individual Plotly figures in the UI. Now finally I'm going to talk about the visualization and the forecasting functions as well. And I'm going to go through this pretty briefly because if you're wanting to do something similar, this might look very different for your use case and for your data. But nonetheless, for the bar chart, we are basically just parsing the data we get from Timescale into our X and Y values for the bar chart, with the dates, of course, being our X axis in this case. And we are also looking at the number of different crypto values that are in the data. Sometimes it's more, like in the Bitcoin and Ethereum volume bar chart. So depending on that, we create multiple series as part of our graph, or traces as they are sometimes called. And so for each crypto in that set, we are going to create a new bar chart, and this is where we put the X axis values, and then in Y the whatever numerical value we are getting here, which we get from this value key in our data. As mentioned earlier, this is the alias that the language model is instructed to use, regardless of whether we're talking volumes or prices here. And then whether it's one crypto or several, we combine these various traces into this one figure, and then we set the layout for that figure. This is where our bar mode goes, which determines whether we stack these various traces or whether we cluster them in the bar chart. This is also where our title goes, the X-axis title as well. This is always going to be dates. The Y-axis. Now this one we could also pass as a parameter from the language model, determining on what exactly is on our Y-axis. But for now, we just have this hard-coded general purpose Y-axis title called value. And then we return the figure. For the pie chart, it's a lot simpler. We don't need the axis here. We just need values and labels. And values, again, we know that we're going to get from this value alias. And then the label is going to be the cryptocurrency symbol. And just with those values and labels, we can create a figure for that, which just includes this one pie chart with those labels and values. We also put our title here, and that's our pie chart. Now finally, the forecast, I think, has the most complexity of them all, because here we also have this separate function to actually get the future values. And here we are basically just doing a bunch of pandas and numpy parsing of the data to fit into these forecasting models that we get from the stats models library. And this especially I won't cover in full detail because I don't think these exact methods are going to be relevant for your use case. But depending on the parameter that we get from the language model, we just use the corresponding forecasting method, get the forecasted values by feeding the data with the forecasting model, some more parsing here, and then we just return the past data as one data frame, and then the forecasted future values as another series. And with these two, just like with our bar chart, we define two traces, one for the past data with the blue line color, and then the other one for the forecast, which is going to be a red dashed line. And then, just like before, we combine these two traces into just one line chart, pass the traces into the data, and include this layout where we again have our title and our axis titles as well. Now, I don't think these exact visualization and forecasting functions are going to be the most important thing for you to take away from this video. I think the number one most helpful concept for you to take away is this idea of structured class outputs from language models, and especially creating these kinds of plans of sequential tasks. The exact functions that are associated with these tasks might look very different in your use case. They might be different visualizations. Here you could just be using a different visualization library, or they might not be visualizations at all. You could be using the same idea for doing some kind of integration planning, for example, that involves calling several different APIs in a sequence, in which case these functions might be different functions for calling different APIs. But whatever it is, I hope this video has inspired you to apply this yourself, apply the ideas in this little demo, and think about what you could be building using these same principles. So with that, I'm gonna wrap up this video here. I do feel like this one might have been a bit more on the advanced side. But I just started working on this concept of data visualization with Timescale and Instructor, and maybe I got a little carried away. So all the more, if you made it all the way through the video, well done to you. And if there's any part of the video or the code that you didn't quite understand, do leave it in the comments below, and I'll try and answer any comments you have. And as always, all the code will be available in the GitHub repo in the description, so you can also take a look at the code yourself. If you want to understand some parts, maybe around the visualizations in more detail, you can always ask ChatGPT. And so best of luck with all of that, and I hope to see you in the next video.